Welcome to this second session of the conference today. I am really glad to introduce our next speaker. Is Alexander Perepechko, and he was going to speak about automorphisms of fine surfaces, Markov numbers, and Thompson group T. Alexander, please, you are very welcome.
Yeah, thank you. I'm very glad to be here. I'm quite grateful to Anton and Anastasia for putting all us together for this opportunity to speak as well. My talk will be quite elementary. I will speak about the geometric connection between these objects. So I hope you see the slides. First object is the Thompson group T of transformations of a unit circle, and its action on the lattice z squared. The second object is the boundary curves on algebraic torus, in particular on algebraic surface, not necessarily torus. And again, the correspondence to Z2. And finally, we apply it to somehow to Markov numbers, but we introduce Markov surface and similar surfaces and obtain something about them. So if any questions, do not hesitate to ask, because I guess everything here should be quite clear. No rocket science. First of all, the definition of the Thompson group, well, we take the Thompson group T. This is the group of continuous, rotation-preserving, piecewise linear transformations of the unit circle. So here the unit circle is just a unit segment from 0 to 1. Its ends glued together. So 0 and 1 are the same point. And transformations such that they are non-differential points, the points of breaking, are dyadic rationals. So the denominator is the power of 2. And the derivatives, the differential points at every other point is an integer power of 2. For example, here are two elements of the Thompson group. They, in fact, generate the whole group. The first element, well, let me draw something. So here it's take here we take from 0 to 1, and we subtract here fourth. So the first derivative is just we send an element to subtract to 1/4. The second element is more interesting because it takes the first half of the circle and shrinks it with the factor of 2 into a quarter, it's the last quarter, and again transforms two other quarters to some other parts, to the first half and to the third quarter here. In fact, we may here we work with dyadic rationals, but we can work with rationals in general. There is a Minkowski question mark function, which exactly provides a correspondence between all rational numbers and dyadic rational numbers. And we can describe this correspondence with the Fourier theory as follows. We take 0 and 1, represent them as fractions with denominator 1, and then apply the following procedure consecutively. We take two fractions, and we take a new fraction with which numerator is the sum of numerators and denominator is the sum of denominators. And we put the new fraction in the middle of the segment, and then again and again and again. So doing this indefinitely for each pair of neighbor fractions, we obtain all possible rational numbers. and we put them at all possible dyadic numbers. So we get this the Minkowski question mark function. In fact, you can this operation of adding fractions is much more natural in terms of vectors. If we send each rational number into a vector with which coordinates are the numerator and denominator, then we get exactly all primitive vectors, but well, not on the whole lattice Z2, but here in the lower half of the first quadrant. Well, it's a start. So we get this cone, the lower half, and we obtain all primitive vectors there. Well, we could start with another cone. For example, we could start with the whole quadrant and apply the same procedure, just take sums of vectors and obtain again all primitive vectors and obtain the correspondence to the dyadic numbers. So in general, to obtain the whole Z2, we must cover it with several cones and use them into Fn. So general picture is as follows. We split the unit circles into segments, into dyadic segments like from 0 to 1/2 or from 1/2 to 3/4, and send each segment to some cone or the complete fan that covers the whole Z2. In this way, we obtain a correspondence between dyadic numbers and primitive vectors. Okay, it works. So an example, here's an algebraic torus. First of all, the algebraic torus is of dimension 2 is k, the base field without 0 squared. We embed it into P1 times P1. And we take natural coordinates on P1 and P1. Well, X is the coordinate of the first copy, so that the point in infinity is just, well, we just denoted by infinity. We just say that X is infinity at that point. And Y is the second copy. And then the complement to the torus consists of 4 curves. So the boundary divisor consists of 4 irreducible components, and we can and we have the dual graph, the incidence graph, where irreducible components are vertices and the intersection points are edges. And this is the most important object in this talk. So it looks like a circle, but it's for now it's just a cycle. And if you look at the automorphisms of the torus, well, the automorphisms. The automorphic group is a semi-direct product of the torus itself, the multiplicative group squared, and the JL2Z group of integer invertible matrices. So the torus itself doesn't act on the dual graph. It doesn't change it, so it acts trivially. But JL2Z somehow transforms the dual graph. We obtain something else. And the question is, what is the action? So how exactly this happens? Well, to answer this question, we have to transform to create a unit circle from our dual graph. We do it with blow-ups. So if we have again two curves, two boundary curves that meet at some point, for example, y equals infinity and x equals infinity, they meet at point infinity, we can blow up these intersection points. And then we can indefinitely blow up all intersection points. And then we obtain all possible boundary curves. And then we have a correspondence between all possible boundary curves and dyadic points on a circle, or again with primitive vectors as E2. We have this correspondence. It preserves its x with sum. So the blowup, the exceptional curve, the blowup of point, goes to a vector that is sum of vectors corresponding to the intersecting curves. In fact, there is a more direct correspondence between vectors and irreducible components. A component corresponding to vector AB meets the closure of the one parameter subgroup. So if we take one parameter subgroup, t power A and t power B, and we take point as infinity, we go exactly to this component, to the inner point of this component after an appropriate number of blows. That's why when you act by automorphisms of the torus, then the initial boundary curves, they go to some four curves on the unicircle. Maybe you have to blow up a lot for that. And that's why if you take not GL to Z but SL to Z, well, the subgroup that preserves orientation of the circle, then you obtain it a subgroup of a Thompson group T. Well, here I said absolutely nothing new, just some geometric picture, which seemed nice to me. So let's look at Markov numbers now. First of all, well, Markov numbers, well, for that we have to remember what is the Markov equation. It's the affine equation introduced by Markov in 19th century. Studied by Markov. It's x squared plus y squared plus z squared equals 3 times xyz. And their positive integer solutions are called Markov triples, and numbers that appear in these solutions are called Markov numbers. Well, we can enumerate the first numbers. There's an infinite number of them. And in fact, we can obtain all possible Markov triples from the trivial one, well, solution 1, 1, 1, by coordinate permutations and by the involution like that, when we send x to 3yz minus x. Why is that? Well, if we take x squared and send it to the right part, the x times 3yz minus x. And permutation, it changes to the terms of the product. That's all. Okay. All Markov triples, when we apply such involutions, they form the binary tree. And if you look at this binary tree, if you apply the involution to the largest number in the triple, you go up, and to others, you go down. And if you look closely, then you may find that each Markov number appears exactly once as the largest number in some triple. This observation, well, is known for more than a century, but it's not yet proven. It's essentially the uniqueness conjecture. And, well, it stands open till now. Okay, so what do we do? What can we do here with the Markov numbers? Well, we introduce the surface of the affine equation is algebraic surface, and we ditch the coefficient 3. It doesn't change anything, and introduce the constant term c. So we have a surface which we call of Markov type. It's an affine surface, but its closure is called the Gaussian tetrahedral surface. Its boundary, it's called tetrahedral because it has symmetries of a tetrahedron. In fact, if you look at lines there, you see a tetrahedron in these lines. Okay, and the boundary infinity consists of 3 contractible lines, and they form a triangle. And again, we can apply the same procedure here. So let me draw something. Well, our lines look like that maybe. And if we look at the dual graph, well, we have something like that. We have a picture which is familiar to us. It's a fan of P2. Okay. So what do? We again take all possible blow-ups. So we get all primitive vectors, and we identify somehow with unit circle. And again, all 3 pictures, they coincide. And here we have the answer to the question about the automorphism groups. Well, using the dual graphs, we prove that the automorphism group is generated by the involution and the coordinate permutation. And this is essentially PGL to Z. Well, I hope that this surfaces of Markov type might be useful for uniqueness conjecture somehow, at some point. Well, I guess that's all. I'll also have a list of literature for the subjects. First of all, if you are interested in Markov numbers, then there is a nice book by Egner on the Markov theorem and the uniqueness conjecture. Second, if you want for Thompson groups, well, first of all, they were introduced and to me by Etienne Guis and Vlas Sergiescu. Well, there is the article which well known, it's in French, and there is also another article on PSL2 there. And finally, if for dual graphs and transformation of algebraic surfaces, all the technique and machinery is contained in the articles by Flanner, Kaliman, and Zalberg, operational transformations of weighted graphs. And I guess that's all that I wanted to say today. Thank you a lot for your attention.
Thank you very much, Alexander. So let us unmute ourselves and thank Alexander for his beautiful talk.